On to a new project. This will be a capacitor leak tester. I'll be using this with my Variac, and this is a very simple schematic, very simple device, and I'm not even sure how well that's going to work. So here's where the power comes in, and then there's the switch. Right now it's shown in the capacitor discharge position. Then when it's in this mode, it puts a 270 ohm resistor across the whatever capacitor you're testing, as well as discharging the filter capacitor inside the unit. Of course, in the on position, it takes that resistor out of circuit. Then it goes through the transformer. The primary on it is 115 volts. The secondary is 250 to center tap and 250 to center tap. So I can either get a 500 volt AC output or a 250 volt AC output. Right now it's connected for 250 volts AC, which when the Variac is run up to 140 volts, it gives me a little over 300 volts AC to the diode. It's not really set up well to test electrolytics. You can, it just takes a while. It takes quite a while for them to bleed off once they finally reach charge, and but you can still do it if you have to test an electrolytic. Most of the time when I'm working on an old radio or a guitar amplifier, if I sense anything that might be wrong with the filter capacitors, I change them out. I don't keep them. The only caps, electrolytic caps I might keep and test would be cathode bypass. That's about it. When I work on old radios, there are quite a few of the old style wax and paper caps. Some of them are really hard to get to. That's one of the reasons I set this up, so I can test those. If they're within capacitance specs and they are not leaky, then they're staying. I'm not changing them. One of the differences in this tester is most of them you're going to see are going to be testing for microamps. And I don't have any meters that will go down to 15 or 20 microamps. So a friend that actually knows about this stuff told me about adding this resistor, and then you can test across that resistor to get your leakage in voltage. Most digital multimeters will easily handle the voltage that you're going to see from this. The calculation goes like this. You divide your test voltage by 500K and multiply that answer by 1,000,000, and that gives you your leakage in microamps. So basically I have 3 test connections. You can see the input voltage. That just tells you what voltage you're testing at. And of course the leak voltage, it gives you the voltage leak, and then the leads that go out to whatever capacitor you're testing. I did a video on most of the component installation, but the lighting was just really bad. And I kind of found out from A-Bomb that LED lighting for these cameras it doesn't work that well. You need softer lighting. I think the guys over at CNC Equipment found the same thing. They do a lot of repairs on heavy equipment, and they do a lot of good videos. They're kind of fun to watch. Speaking of CNC, I'm getting ready to go ahead and do the labeling on the front panel. I just engrave it. Now, when I said CNC Equipment, that is not CNC, it's C and C. You won't find them if you try to look for CNC Equipment. C and C. So anyway, I'm just engraving where all the labels go, and what I'll do after this is I'll clean it off real good, and then I'll put a coat of lacquer and try to seal it up, and then shoot some black paint in there and into the labeling, and then I just wipe off the excess with lacquer thinner, and it comes out pretty nice. I tried it without first coating it with lacquer, and the paint bled in under this UV coating that is on this Baltic birch plywood. It's a nice coating, but the it looked terrible when I tried to clean it off. I'm going to skip ahead here in a second, and because this gets boring. If my speech sounds a little funny, I just had a tooth pulled, so I'm sounding a little challenged. I don't want to say the other word I was going to say. Yeah, you still can't see it very well with this lighting. It's very difficult to see that. You can see here I already sprayed the black in there and cleaned it all off. Now I'm going to go ahead and put in the holes for all the test leads and the switch. When I did that on the first one, the bleed through from those holes was the worst, from the black paint bleeding in under the UV coating. So I decided to go ahead and get all that done first, then I'll go ahead and cut the mounting holes for everything. I also changed to a softer light. I'm going to go ahead and jump ahead a little bit on this. This kind of gets boring too. Once this is done, I have to flip this over to the other side and cut the relief for the all the components. The plywood's it's just under 1/2 inch thick, and it's too thick for most components. So I have to make sure that that I cut relief in behind each one of these sections. I use registration pins on here, so when I flip it over, the router knows where everything is within a few thousandths. I'm not going to leave it on here too long either. Same reason, this gets boring after a while. I'll just cut out this one relief hole, and then I'm going to jump ahead. This last one is where the switch mounts. I'm going to test fit some components. I had to go back and open up the that hole in the center there. I have a lamp going in there, and I didn't quite make it big enough, so I had to take it back out and open up that hole just a little bit. Got the cord connected, and I'm going to go ahead and put the rest of the case together and do some testing. All right, we're going to test this old electrolytic, and I already know it's out of spec. It's a 20 microfarad, and it tests at 37, but we're going to test for leakage. So it's 450 volts, so I'll use my 140 volt scale on the Variac, and then I can get about 425 volts, so it's close enough. So I'm running it up now, and we're pretty much peaked out on voltage, and you can see the voltage over here on the test, and it's staying up there pretty high, but they suggest you give it 5 minutes, so that's what I'm gonna do. I'm gonna cut it off and then bring it back after 5 minutes. So there's 5 minutes, and it's still 407 volts. Okay, this obviously is a leaky capacitor, so but I already knew it was bad, but I wanted to see how this thing reacted to it. Okay, this one is what I presume to be a good electrolytic. It's 3 microfarad at 250 volts. So I can go back to my lower scale on the variac and run this up to its operating voltage, which is what you're supposed to test these at when you're testing them this way. The specs they give you on the data sheets, they expect you to test it at voltage. So you can see it's still up there pretty good, but it's coming down pretty quickly. And I'm gonna do the same thing. I'm gonna take you out of here, and then we'll come back after a few minutes and see what it reads. So right now it's reading, you can't see it very well, but it's reading about 2.5 volts, and it's kind of bouncing around there. So that's what we'll call it 2.5 volts. And usually how I shut this down is I turn the voltage to 0, and then flip it to discharge, which discharges that capacitor. You notice some negative voltage, in a fair amount of it. I don't know what that's from. Here's another 3 microfarad at 250, although it's not an electrolytic, it's probably a propylene. So we're going to run this up, and you're going to notice that when I look over at the test meter, that's already to 0, which is how these should be. There should be no leakage on these. It started out with a little, but it went down quickly. So I'm going to play with the range settings on here and see if I can detect anything at all. But what happens is you get down there in the range and it kind of bounces back between negative and positive. So that's just problems with the issues with the meter. So that's effectively no leakage on that capacitor. Now I'm gonna see if I can get some ohms, an ohms reading, a resistance reading out of that bad electrolytic, and I can. It's not a capacitor anymore; it's a 15 meg resistor. You can see. So I decided to go ahead as a comparison, check that other electrolytic that we know is good, and it's basically an open circuit. I'm testing it on the 20 meg scale, and it shows nothing. So yeah, I think that other one's a goner. You remember we talked about the way to convert that voltage result that we got into microamps. And that is the formula. You start with your leak voltage, which was 2.5. You divide that by the resistance, which is 500K. And then you multiply that times 1 million, which gives you microamps. And that is our result. We are leaking 5 microamps. Now, how do we know that's okay? So we go to the data sheet on an F&T cap, and it shows here, this is how you calculate the acceptable leakage. That is 0.008 times nameplate capacitance times nameplate voltage plus 4, which equals 10. Our capacitor calculated out at 5 microamps, which is well below the acceptable limit. I doubt this will be the end of it, because I can already think of a few things I'd like to change. But I would really like to hear from some actual experts on this that can give me their view of how this thing works. Okay, thanks for watching.